Welcome back, Gators! Here we go with a discussion of the energy curve, the potential energy function, and how we can find out lots of neat things. Let's get going! So, in order to discuss the relationships between potential energy and force, we're going to review a couple of relationships. We already know these, but I just want to bring them back to the forefront of your memories. So conservative work changes the potential energy, and that's what we have here. Conservative work changes the potential energy. Now this stuff in the middle is if the force changes based upon where you are, then we need to do that calculus stuff. So the work that's done by the conservative force is equal to this, and that changes the potential energy. Well, breaking out this important relationship here and swap the minus sign over, we have the potential energy is equal to the negative of the conservative work. If we take the derivative of both sides, what we end up with is the force is equal to the derivative of the potential energy function with respect to x, but in the negative direction, which is what we expect. Conservative forces will cause the potential energy to change. That's what this all means. The hard part about this is usually not taking the derivative, because you're pretty good at that. It's remembering to include the negative sign. Okay, so word to the wise, remember the negative sign. Now, this looks really scary because there's some new notation in there, but really the operation that you're going to do here is easy. Okay, it's just taking a derivative. So what it's saying is that if you have a force with respect to a three-dimensional position, it's equal to the negative of the derivative of the potential energy function in 3 dimensions with respect to position. Well, if the potential energy depends upon x, y, and z, your location in that 3-dimensional Cartesian coordinate system, x, y, and z, then the force is going to be applied in those 3 dimensions as well. Potential energy is a scalar, meaning there isn't direction, but force is a vector, meaning there is. So the way to convert from scalar back to vectors is by doing an operation called taking the partial derivative. And what it does is it isolates each dimension from the other, and we can find out the component of the force in the dimension of interest. And that's what this means. This says the partial derivative of the potential energy function with respect to x. Well, so this says take the derivative of the potential energy function, but only x is a variable. If there are y and a z in the function, you treat them as constants, just as if they were a or b. You ignore them as... Okay, so let's maybe take a look at an example here. So if u of r is equal to, let's say, 3xy plus 2y squared z. And I want to find out what the force is acting on an object that is at, say, a position 1, 2, 3. So in the x direction, a unit of 1, in the y direction 2, and then in the z direction 3. What is that equal to? Okay, well, this formulation over here says that I need to take the partial derivative with respect to x to find the x component. Well, what exactly is the partial derivative with respect to x? Okay, so it says, well, take the derivative of this, but y is a constant. So it's 3y times, what's the derivative of x? Well, the derivative of x with respect to x is 1, so this would be 3y. Y is a constant. So you treat it the same way you do the 3. Plus, with respect to x, there are no x's here, so all of this is a constant. Well, what's the derivative of a constant? Well, it's 0. So this is the x component of the force, is 3y. Well, let's do in the y direction. Oh, let's not forget that minus sign. Miller, you almost did it, so that makes that a negative. Okay, so I'm going to put the negative out there right off the bat to remember it. Okay, so we're going to take it with respect to y. Well, that means that x is a constant, so the derivative of y is, the derivative of y with respect to y is 1, so we end up with 3x. Now, z is a constant, so we have 2z times the derivative of y squared. Well, that's 2y. So we have 2 times 2 times yz. So that would be plus 4yz. Okay, and then doing in the z direction. Partial of the function with respect to z. Okay, no z's in that term, so that's a constant, it's 0. We have a z in the second term. Well, 2y squared is a constant times the derivative of z, which is 1. So our z component is 2y squared. Remember the minus sign. Now let's put this all together so it looks like this. Well, our force is equal to, and this is a vector, so I'll put the little arrow over it because I can't draw in bold, is take the x component times the I unit vector, and that was negative 3y, so negative 3 times y I. And then the y component is negative 3x minus 4yz. So it's negative 3x. Well, I'm going to put a plus sign in and just do it this way so I don't screw up the signs with distribution. 3x plus 4yz, and that's in the j direction. And then in the k direction, we have minus 2y squared and k hat. Now, my original problem was, well, what's the force when x is 1, y is 2, and z is 3? Well, that would be, we substitute in 1 for x, 2 for y, 3 for z. So the x component would be negative 3 times 2, which is negative 6. In the y component, 3 times 1 is 3, plus, okay, I made a mistake up here. Did anybody catch it? That should have been a minus. Okay, now we're all set. So it's going to be minus whatever the inside of this is. 3 times x is 3 plus 4 times 2, which is 8, times 3, which is 24. Okay, so we have 3 plus 24, so that's minus 27j. And then our z component is 2 times 2 squared. So that's negative 8, minus 8k. Well, that's the force on an object when it's located at this position. If we wanted to find the magnitude of the force, we would use the three-dimensional Pythagorean formula. 6 squared plus 27 squared plus 8 squared, and that would give us the magnitude of the force. The IJK notation gives us the direction. It's a little fussy. You need to spend some time doing it, but it's not particularly hard. Keep track of your minus signs. You've seen me struggle with that. Okay, next up. We're going to actually look at potential energy functions and determine things like the kinetic energy at a location, the total energy of a system, based upon what we know about how the potential energy behaves. Well, on this diagram here, potential energy is the blue. And this is for either a pendulum or a spring. They have a similar potential energy type graph. So when our spring is fully compressed, we're at our maximum potential energy and we have no kinetic energy because it's not moving. But as the spring starts moving towards equilibrium, the potential energy is decreasing, but because of conservation of energy, the kinetic energy is increasing. It's going faster and faster. And then, because of inertia, the spring continues on, and the potential energy is increasing because the spring is getting stretched until the spring reaches the extent. We call that a turning point. The spring turns around and then repeats the motion backwards. It oscillates back and forth. And on this graph, we can see that the furthest that we're going to go to the left is right here. We stop moving there. And over here, the furthest to the right that we're going to go is right here. We call these points where the total energy intersects the potential energy, we call that a turning point. The object can't go past that. Okay, the mathematical function can, but the object can't. Okay, let's look at this in practice. Okay, so here's some graphs. The red graph, the red lines are potential energy function, and the left and right graph are the same graph. They just have a little bit different information on it. And then the blue graph is a force graph, which is the derivative of the potential energy function, but opposite, negative of that. Okay, so let's look at the upper left-hand graph. I have to give you some information for you to use this graph. I either have to tell you what the maximum mechanical energy is. In this case, that's what was given. That's 5. That's 5 joules. That's as much energy as we can have. So that means that anything to the left of x1 is not physically possible. The object can never be over here. Okay? And we call that point a turning point. If the object was moving to the left, it would reach the turning point and would no longer have any kinetic energy. It would have the maximum energy it had, and it would all be in potential. So it would turn around and go back the other direction. And when it got to this point, it would keep on going because it has kinetic energy and it's less than the total mechanical energy, so it can keep on going. Okay, another thing that we can tell from this. Well, if we know this is our maximum energy and it's at 5 joules, and up here we have 5 joules of potential energy, when we go down here, the potential energy is 0, which means that we must have 5 joules of kinetic energy. And this is due to conservation of energy. And I'm going to write the formula for it. So we have mechanical energy is equal to U plus K. This is a constant. In our case, it's 5. So we read potential energy off of the graph, and we determine the kinetic energy based upon this relationship here. Now, quick look at what unstable, stable, and neutral equilibrium are. It's kind of easy to visualize if you think of this as a roller coaster. If your car is at the top of the roller coaster and in equilibrium, means the net force is zero acting on it, and let's say you're at rest up here. A nudge in one direction or the other would send you to the bottom to a much lower potential energy. That's called unstable. Okay, your object does not want to stay in that position. It's in equilibrium, but it has more potential energy than it knows what to do with. Okay? If we're down at the bottom of the dip, if we at rest here at x4, we give it a little nudge, it's going to oscillate back and forth, always coming back to the equilibrium point. If we're up here on the level, on the flat, a little nudge to the right is going to send the object to the right, and it's going to keep on going at constant speed. It's in equilibrium, but it's moving. Okay? So we have unstable equilibrium, we have stable equilibrium, we have neutral equilibrium. We have static equilibrium, which is a class. It means that the object's not moving. And you can be unstable, stable, or neutral if you are static. If you are in kinetic, you can be, or I'm sorry, not kinetic, it's called dynamic motion. If you're in dynamic, it means that you're moving. You can be in unstable, stable, or neutral as well. Next up. Okay, here's a good example of how to use an energy graph to find out some information. Previously I said that we needed to be given some information about the object, either its total mechanical energy or we needed to be able to find out its kinetic energy at a point. And in this problem, they've given us the information to find the kinetic energy. Okay, so what it says is we have a 2 kilogram particle, and that when it's at 2 meters, it has a velocity of negative 1.5 meters per second. Well, from that information, I can find out what the total mechanical energy is. Well, at 2 meters, 1, 2, that's this point right here, I see is negative 5, 6, 7, 8. So that's negative 8 joules plus the kinetic energy, 1/2 the mass, which is 2, times the speed, which is 1.5 squared. Well, this is negative 8 plus 1/2 times 2, which is 1. And 1.5 squared is 2.25, which gives us a negative 5.75 joules. That's our maximum energy. Okay, so 5.75, I'm going to draw my maximum energy right here, negative 5.75. Okay, I'm going to notate it M, E. Well, let's do the same notation. Mechanical energy is equal to negative 5.75 joules. Well, this has just been preparation work. Okay, it'll help us later on answering C and D. Okay, let's go ahead and answer A and B. What is the direction, or what is the force and its direction at this point? Well, I told you earlier that force is equal to negative du dx. And because this is linear, we just find the slope of that line. So the force is equal to negative u2 minus u1 over x2 minus x1. Okay, so let's go ahead and pick the point that they gave us, and that was u1 was -8, and x1 was 2. Let's pick another point. We can pick any of these points. Let's go ahead and pick this point right here, 15, 16, -16. And x is 3.5. And we end up with a slope of 5.33. Okay, and it's negative, and this is, the slope is negative, but then we do the negative sign on that, so it's 5.33 newtons. Okay, the slope is negative 5.33, but the force is positive 5.33. So that means that the force is pointing to the right, it's in the positive direction, and it has a magnitude of 5.33 newtons. Next up, let's find out if it can go to the, or we want to find out what the turning points are. So we want to find out what the location of that is and what the location of this is. And I'm only going to do the left one and leave the right one up to you. Well, this is a line, and I want to find a point on the line. I know the slope, I know at least one point, and I want to find the other point. Okay, so I'm going to use the point slope method to find the equation of the line and ultimately the position that I'm looking for. Okay, so we have -5.33 is equal to, well, I know the potential energy at this point. It was -8 minus the energy at this point, which is -5.75, all over x2, which was 2, and we're looking for x1. Okay, so now it's just a matter of doing the algebra, and I will also leave that up to you. I think you'll find it's somewhere between 1 and 2. Okay? Now, what is the speed at x equals 7 meters? Well, 7 meters is right here. And it says that we have a negative, let's see, we have 5, 10, 15, negative 17 joules of potential energy. So if we have a negative 5.75 joules of mechanical energy, and we have a negative 17 joules of potential energy, what's our kinetic energy? Well, let's see, that would be kinetic energy is equal to 11.25 joules, and that's equal to 1/2 times the mass, which is 2, times v squared. Well, 1/2 times 2 is 1. V squared, to unsquare it, we take the square root. So v is equal to the square root of 11.25, which is equal to 3.35 meters per second. Okay, so there's a lot of information in there. It's a long problem. Please work through and find the other information that you need, and we'll move on. Here's your multiple choice question. Welcome back. I'm going to do an example problem and then give you another free response problem. Let's move on here and do this problem. The potential energy of a two-particle system separated by a distance r is given by the potential energy is equal to constant A over r, and we want to find the force. Okay, so force is equal to negative du dr. Well, if u of r is A over r, it's the force is equal to the negative of the derivative of A. Well, 1 over r is the same thing as r to the minus 1 du, or I'm sorry, dr. Okay, and from the derivative rules, this becomes negative 1 times A r, and we reduce, which is negative 2, and that's our function with the minus sign in front. Okay, so it becomes A r to the minus 2 or A over r squared. And this is actually your free response question. Good luck. But I'm not ready to see you next time. Okay. I'm going to hold these up on the screen for just a little bit. Go ahead and pause, and I'd like you to work it. Work the problem and compare your answers to what I show you after a second. These are your answers. Next part of the problem. That's your answer. Final part of the problem. Check your answers. Now, I'll see you next time.